In geometry, stellation is the process of extending a polygon, polyhedron in 3 dimensions, or, in general, a polytope in n dimensions to form a new figure. Starting with an original figure, the process extends specific elements such as its edges or face planes, usually in a symmetrical way, until they meet each other again to form the closed boundary of a new figure. The new figure is a stellation of the original. The word stellation comes from the Latin stellatus, starred, which in turn comes from Latin stella, star. Kepler's definition. In 1619 Kepler defined stellation for polygons and polyhedra as the process of extending edges or faces until they meet to form a new polygon or polyhedron. He stellated the regular dodecahedron to obtain 2 regular star polyhedra, the small stellated dodecahedron and great stellated dodecahedron. He also stellated the regular octahedron to obtain the stello-octangular, a regular compound of 2 tetrahedra. Stellating polygons. Stellating a regular polygon symmetrically creates a regular star polygon or polygonal compound. These polygons are characterized by the number of times m that the polygonal boundary winds around the center of the figure. Like all regular polygons, their vertices lie on a circle. M also corresponds to the number of vertices around the circle to get from one end of a given edge to the other, starting at 1. A regular star polygon is represented by its Schläfler symbol, n per meter, where n is the number of vertices. M is the step used in sequencing the edges around it, and m and n are co-prime. Making m equals 1 gives the convex n. If n and m do have a common divisor, then the figure is a regular compound. For example, 6/2 is the regular compound of 2 triangles, 3, or hexagram, while 10/4 is a compound of 2 pentagrams, 5/2. Some authors use the Schläfler symbol for such regular compounds. Others regard the symbol as indicating a single path which is wound m times around n per meter vertex points, such that one edge is superimposed upon another and each vertex point is visited m times. A regular n-gon has 2 stellations if n is even, and 2 stellations if n is odd. Like the heptagon, the octagon also has 2 octagrammic stellations, one, 8/3 being a star polygon, and the other, 8/2, being the compound of 2 squares. Stellating polyhedra. A polyhedron is stellated by extending the edges or face planes of a polyhedron until they meet again to form a new polyhedron or compound. The interior of the new polyhedron is divided by the faces into a number of cells. The face planes of a polyhedron may divide space into many such cells, and as the stellation process continues, then more of these cells will be enclosed. For a symmetrical polyhedron, these cells will fall into groups, or sets, of congruent cells. We say that the cells in such a congruent set are of the same type. A common method of finding stellations involves selecting one or more cell types. This can lead to a huge number of possible forms, so further criteria are often imposed to reduce the set to those stellations that are significant and unique in some way. A set of cells forming a closed layer around its core is called a shell. For a symmetrical polyhedron, a shell may be made up of one or more cell types. Based on such ideas, several restrictive categories of interest have been identified. Mainline stellations. Adding successive shells to the core polyhedron leads to the set of mainline stellations. Fully supported stellations. The underside faces of a cell can appear externally as an overhang. In a fully supported stellation there are no such overhangs, and all visible parts of a face are seen from the same side. Monoacral stellations. Literally, single-peaked, where there is only one kind of peak, or vertex, in a stellation. The stellation is monoacral. All such stellations are fully supported. Primary stellations. Where a polyhedron has planes of mirror symmetry, edges falling in these planes are said to lie in primary lines. If all edges lie in primary lines, the stellation is primary. All primary stellations are fully supported. Miller stellations. In the 59 icosahedra, Coxeter, Duval, Flather and Petrie record 5 rules suggested by Miller. Although these rules refer specifically to the icosahedron's geometry, they have been adapted to work for arbitrary polyhedra. They ensure, among other things, that the rotational symmetry of the original polyhedron is preserved, and that each stellation is different in outward appearance. The 4 kinds of stellation just defined are all subsets of the millistellations. We can also identify some other categories. A partial stellation is one where not all elements of a given dimensionality are extended. A subsymmetric stellation is one where not all elements are extended symmetrically. The Archimedean solids and their duals can also be stellated. Here we usually add the rule that all of the original face planes must be present in the stellation, i.e., we do not consider partial stellations. For example, the cube is not usually considered a stellation of the cube octahedron. Generalizing Miller's rules, there are 4 stellations of the rhombic dodecahedron, 187 stellations of the triachus tetrahedron, 358,833,097 stellations of the rhombic triacontahedron, 17 stellations of the cube octahedron, unknown number of stellations of the icosahedron. There are 7,071,671 non-chiral stellations, but the number of chiral stellations is unknown. 17 of the non-convex uniform polyhedra are stellations of Archimedean solids. Miller's rules in the book The 59 Icosahedra, JCP. Miller proposed a set of rules for defining which stellation forms should be considered properly significant and distinct. These rules have been adapted for use with stellations of many other polyhedra. Under Miller's rules we find there are no stellations of the tetrahedron, because all faces are adjacent. There are no stellations of the cube, because non-adjacent faces are parallel and thus cannot be extended to meet in new edges. There is 1 stellation of the octahedron, the stello-octangular. There are 3 stellations of the dodecahedron: the small stellated dodecahedron, the great dodecahedron and the great stellated dodecahedron, all of which are Kepler-Poinsot polyhedra. There are 58 stellations of the icosahedron, including the great icosahedron, and the second and final stellations of the icosahedron. The 59th model in the 59 icosahedra is the original icosahedron itself. Many Miller stellations cannot be obtained directly by using Kepler's method. For example, many have hollow centers where the original faces and edges of the core polyhedron are entirely missing. There is nothing left to be stellated. On the other hand, Kepler's method also yields stellations which are forbidden by Miller's rules since their cells are edge or vertex connected, even though their faces are single polygons. This discrepancy received no real attention until Inchbald. Other rules for stellation. Miller's rules by no means represent the correct way to enumerate stellations. They are based on combining parts within the stellation diagram in certain ways, and don't take into account the topology of the resulting faces. As such, there are some quite reasonable stellations of the icosahedron that are not part of their list. One was identified by James Bridge in 1974, while some Miller stellations are questionable as to whether they should be regarded as stellations at all. One of the icosahedral set comprises several quite disconnected cells floating symmetrically in space. As yet an alternative set of rules that takes this into account has not been fully developed. Most progress has been made based on the notion that stellation is the reciprocal or dual process to faceting, whereby parts are removed from a polyhedron without creating any new vertices. For every stellation of some polyhedron, there is a dual faceting of the dual polyhedron, and vice versa. By studying facetings of the dual, we gain insights into the stellations of the original. Bridge found his new stellation of the icosahedron by studying the facetings of its dual, the dodecahedron. Some polyhedronists take the view that stellation is a two-way process. such that any two polyhedra are sharing the same face planes as stellations of each other. This is understandable if one is devising a general algorithm suitable for use in a computer program, but is otherwise not particularly helpful. Many examples of stellations can be found in the list of Wenninger's stellation models. Stellating polytopes. The stellation process can be applied to higher dimensional polytopes as well. A stellation diagram of an n-polytope exists in an n-dimensional hyperplane of a given facet. For example, in force space, the great ground stellated 120 cell is the final stellation of the regular 4-polytope 120 cell. Naming stellations. The first systematic naming of stellated polyhedra was Cayley's naming of the regular star polyhedra. This system was widely, but not always systematically, adopted for other polyhedra and higher polytopes. John Conway devised a terminology for stellated polygons, polyhedra and polychora. In this system, the process of extending edges to create a new figure is called stellation. That of extending faces is called greatening, and that of extending cells is called aggrandizement. This allows a systematic use of words such as stellated, great, and grand in devising names for the resulting figures. For example, Conway proposed some minor variations to the names of the Kepler Poinsot polyhedra, stellation to infinity. Wenninger noticed that some polyhedra, such as the cube, do not have any finite stellations. However, stellation cells can be constructed as prisms which extend to infinity. The figure comprising these prisms is a stellation to infinity. By most definitions of a polyhedron, these stellations are not strictly polyhedra. Wenninger's figures occurred as duals of the uniform hemipolyhedra, where the hemi-face is dualized to vertices at infinity. From mathematics to art. Alongside from his contributions to mathematics, Magnus Wenninger is described in the context of the relationship of mathematics and art as making, especially beautiful, models of complex stellated polyhedra. The Italian Renaissance artist Paolo Uccello created a floor mosaic showing a small stellated dodecahedron in the Basilica of St. Mark, Venice. 1430. Uccello's depiction was used as the symbol for the Venice Biennale in 1986 on the topic of art and science. The same stellation is central to two lithographs by M. C. Escher, Contrast, 1950, and Gravitation, 1952.